Hey everyone, Balaj here, and welcome to episode 2 of the KZ Restomod. Today we'll be looking at how to upgrade the original Kawasaki front disc brake rotor and go to the KTM Duke 390 disc rotor, which is significantly bigger. As well as the front brake upgrade, I'll also be looking at how to graft the rear caliper onto the build as well. Since the final weight of this build should be a bit less than the Duke 390, I've decided to stick with the OEM KTM brakes. The new caliper will see the bike go from an old single piston axial to a 4-piston radial caliper on a significant larger rotor. This should improve braking performance by orders of magnitude. The new caliper will also be half a kilo lighter, so it should help reduce unsprung weight from the front end.
Now, unfortunately, the PCD of this thing will absolutely not fit the Kawasaki wheel. They are completely different. So there's only a couple of ways I could see of doing this, and the first one is to get a rotor blank, redesign it with the correct PCD and the right holes, and then get it recut. Unfortunately, as I found out, the position of where the actual disc mounts to relative to the brake caliper is actually quite different on the Kawasaki wheel and didn't line up correctly, so there is actually an offset that needs to be dealt with as well. So the second option, which I ended up going with, was to actually buy a 2-piece rotor replacement for this, drill out the center, redesign the center with the correct PCD, the correct offset, and the correct size center hole, and then put it all back together with some aftermarket bobbins. So now that I've got the center of this 2-piece rotor drilled out, what I can do is take my measurement for the diameter across here, and also grab the PCD off the Kawasaki rim as well as the inner hole, and then work out what the offset needs to be and design a brand new shiny central carrier.
So with the brakes being a major safety component, I wanted to make sure that the parts I designed weren't going to fail. So I wanted to include a bit of stress analysis as part of the process. So I spent a fair few days trawling through engineering books. Unfortunately, most of the things I came across were more about designing brakes from scratch and actually sizing everything. This project, it was more about reverse engineering existing brakes that were already on a bike. So
I decided to go back to first principles and try to simplify the approach with the information we already have. Since we know the weight, the 100-kilometer stopping time and distance for the Duke, we can use the equations of motion to work out the deceleration rate. This can be used to further calculate the force needed to decelerate the bike and rider. With a few other variables like rolling resistance, wheel diameters, and wheel torques factored, I was able to calculate some indicative braking torque values for use with my FEA. Then all of this was moved over to a spreadsheet to make adjustments quicker and easier. I used the original 2-piece center as a guide for the thickness of the spokes and the outer ring, because the original part should have already been through a full design process and be appropriately sized, although I did widen the spokes on my design for a better visual balance with the attachment points on the rotor. I chose 7075 T6 aluminium for the part because this grade has excellent mechanical properties, with yield strength coming in between 470 and 500 MPa. I converted the brake torque back to a force that would load the contact patch for the brake pads on each side of the rotor. This was done at a few positions around the disc with similar results all around. One of the main results I look at for FEA is the safety factor. This number shows what multiple of the simulation load the part can safely withstand without starting to fail. I couldn't find any standards or consistent guidance here, so I decided to be conservative and aim for somewhere between 2 and 3. I did also reach out to Brembo and a few other brake manufacturers for help with brake torque targets and safety factors, but I was pretty much stonewalled at every turn. The analysis approach I used may not be completely right, but it wasn't for lack of trying. We also want to look at the amount of flex that a part has with the deformation results. 0.06 mil is practically non-existent, so I'm pretty happy with that. It took about 12 hours to print this part, so I left it to run overnight. I had to make a few small adjustments to the design after the first test print. second print worked perfectly, so I packaged up the drawing and sent it off with the step file for CNC milling. Once the newly milled center arrived, I temporarily put it all back together with the original bobbins from the drilled out rotor to test the fitment. And it looks awesome. There's also a pretty decent weight saving in upgrading the brakes. Together with the calipers, there's almost a 1 kilo difference.
How good does that look? That's a pretty significant upgrade on what was there before. So by using this hub motor, we've also now automatically got a disc brake that we need to deal with as part of the build. And in keeping with the whole KTM theme, I've opted to go for the rear brake caliper from the Duke 390 as well. So here we have the rear caliper mount from the KTM. And the way this works is the axle goes through this round hole here. Then you've got a cutout which basically locks into the inside of the swing arm. And then the 2 holes here is where the caliper actually rides. So this would normally sit from the axle inside the swing arm on the other side. Now with this setup, with the 440, there's not a huge amount of space there, so that's absolutely not going to work. So the clearance isn't there because of all the bolts and the brackets. The suspension also gets in the way, so to make this work, the bracket will need to be redesigned. In the end, I decided to do a low mount caliper. So that means the bracket will drop the brake caliper down roughly around here, and there'll be an attachment point a little bit forward of that to take advantage of the original torque arm. The reason I kept using the torque arm as part of the design for this caliper bracket is that I didn't want to lock the caliper in at the end of the swing arm like a lot of the modern bikes. The reason for that is that that would introduce a bending moment under braking. Now with these older bikes having stereo suspension, the swing arm is fully supported at the back, so there's very little load actually put into the swing arms, which is why they made these swing arms out of such a thin steel tube. But that also means we can't then load this thing in any funky ways that would introduce moments, and we have to use that torque bar to triangulate the braking loads back to the strongest point on this arm, which is just near the pivot. So it looks like I may have made a rod for my own back by choosing this rear caliper. It is an axial type rather than radial, so the mounting for it is pretty complicated. I've had to spend a lot of time going through and actually modeling the bracket and making sure that everything aligns correctly.
The first step in reverse engineering this bracket was to set up a basic analog to get the pin distances and the main cutouts right for the caliper. I made about 5 variations of this part, and this was the final 3D printed piece with the correct dimensions and pin distances.
So this is an example of a 3D printed mock-up that I used to get the position of the caliper correct. And it basically just slides up and over the axle. You can mount the caliper to that and also attach the torque arm to that front tab. And so I was able to print these off quite fast because they're only a couple of layers with a pin. So basically a 1 hour print, nothing too complicated.
Once I was happy with the dimensions of the mock-up, it was time to commit to extruding the actual part. I made a basic representation of the brake disc and the caliper as a single piece and pinned it together with the bracket. This was used with the talk about the axle to load the model. I'm fairly sure that the stress concentrations around the edges of those holes where the caliper rides are singularities. This is a fairly simplistic analysis, but my focus is really on that torque arm attachment and making sure it doesn't fail. The fitment was spot on, so I sent the design off for CNC milling.
this is the finished product for the rear caliper mount, all put together with the caliper. Nice anodized finish on the 7075. Turned out really well.
The original wheels used a removable axle which could slide through the swing arm holes from one side to the other. The hub motor has a fixed axle, so this installation method doesn't work, and the swing arm needs to be opened up so the whole unit can be slid into place. I'd already slotted one side, but once the tire goes on and the brake caliper is mounted, there won't be enough wiggle room to maneuver everything into position. Both sides of the swing arm then had to be opened up for a smooth install. Since the swing arm won't properly secure the axle once everything's cut open, I designed some keyed brackets that will lock it all together properly using the lower shock absorber bolt. A secondary spacer and the primary keyed brackets locked together to keep the whole assembly properly centered. I didn't account for quite how thick 2 layers of anodized finish would be on the bracket, so the fit was a bit tight on the axle. I'll look at removing the anodization in the axle hole once I put the bike together properly. And here's the whole thing test fitted. It looks super clean, almost OEM. I'm really happy with how this turned out.
Thanks for watching, and if you liked today's video, don't forget to smash that like button and subscribe for updates on our next episode. On the next episode, I'll be talking about the battery pack, the battery management system, as well as the charger, so stay tuned for that one.